Welcome to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from CycleComputing. We have the CEO of the company, Jason Stowe. So, Jason, welcome to the show. I wanted to ask you about this new record size instance you guys spun up on AWS. This was a pharmaceutical run. In the space of 2 hours, you ran up, it says 10,600. Is that nodes or instances, or what's that number?
It's 10,600 instances, and to give you an idea, the 50,000 core run that we did before was actually 6,700 instances. So there were two really primary facets about this. Is A, we were able to get a heck of a lot of hosts out of AWS in the first place, and make functional use of them, actually make them productive. And then the second piece is that, and this is in a spot instance environment where nodes are coming and going all the time, et cetera. The 30,000 core run that we did, that Novartis later took credit for about a year and a half ago, when we talked to you about that one, was actually a spot instance run as well. So it's essentially taking advantage of those nodes where you bid for how much you're willing to spend on the compute. And then the other parts about this are the science essentially is running millions of compounds against a protein target that's affiliated with cancer, but outside of which form of cancer and who the end user is, the only thing we're allowed to say with the customer at this point is that they're a Big Pharma. And so it's essentially a very strategic form of research, trying to find potential molecules that might lead to drug candidates that might lead to actual treatments affiliated with a given protein that's related to cancer. Essentially, they're trying to either inhibit or enhance the function of that protein, and that's what the science being done was.
Okay, Jason, so as part of this, you talked about using the Chef 11, and I haven't heard you guys talk about Chef in the context of these kind of big runs before. Was this a new piece of software for you to use?
Well, so we actually have been using Chef for quite some time to do software configuration on the clusters. So we write a lot of software that creates and deploys, or what we refer to as orchestrates the HPC workload. And that software essentially is responsible for a lot of pieces of the stack, basically making the scheduling environment scale, moving the data around, making things secure, keeping track of encryption keys, making that audible and reporting and doing monitoring. But the software configuration piece of these clusters, for quite some time, we've used Chef servers as a way of being able to have the nodes check into a central location, make sure they're using the exact right software at the right time to run. And part of the interesting piece about that is that in the past, when we did like the 50,000 core run, we would have to use 10, 15 Chef servers to manage the deployment of software across, for example, the 6,732 nodes that were in the 50,000 core cluster that we did with Schödinger this past year in mid-2012. In this run, we were actually able to use a single Chef 11 instance, and it's really exciting. Basically, the Chef infrastructure got rewritten from Ruby to Erlang. And it also got ported from using the CouchDB to using PostgreSDB. And so PostgreSQL and Erlang both contributed to a tremendous scalability improvement. And we were just really excited because the ops guys called us up and said, look, we think we can hit 10,000 servers on this run. Do you have a workload that would be able to use this kind of infrastructure? And as it happened, we had this cancer science that was basically being done by a client of ours. And so we connected the two, and simply put, Chef scaled. It did a great job. So our software essentially was responsible for orchestrating all of the HPC environment and getting the workload running and tracking it and reporting and audit and security and so on and so forth. But the software configuration we were able to handle through a single Chef server instance running on a CC2 instance in Amazon, without any additional work or any load balancing or anything along that line. That one server handled the whole load.
Now, you did this on the EC2 instances, is that correct?
Yeah, that's right. So we used essentially 10,600 multi-core EC2 instances to compose the cluster. The workload itself is a standard kind of high throughput workload on the outside. So it's essentially a needle in a haystack problem where we're trying to help a researcher find molecules that may interact positively with a target, a region on a protein that in this case is affiliated with cancer, so that they can potentially get compounds that might inhibit or enhance the function of that protein. And so essentially, AWS was the source for infrastructure for all of that compute. We used Amazon EC2 to basically gather over a 2-hour period this 10,000 server or 10,000 instance environment.
And then in your blog, Jason, you talk about how big a room you would need to just contain a compute cluster of this size. Can you tell us more about that?
Yeah, we were a little bit uncertain as to how to communicate the scale of a 10,000 server environment. So we actually reached out to a few different analysts, including some of the guys from IDC, around, if we looked at a modern, Fortune 500 company and looked at their data center that had 10,000 servers in it, what would it look like? And the answer they came back with was that it would be a 12,000 square foot facility, so it'd be a 12,000 square foot data center, and the cost of operating both the compute and that facility would be a $44 million investment, essentially, to create that kind of 10,000 server environment. And instead, on Amazon, we were actually able to do this. We created the environment instead of it being, months or years, depending on how long it takes you to plan and break ground and build a data center and so forth. We created the environment in about 2 hours, and then used it for an additional 9, and turned it off. And after that period of time, that 11-hour period, essentially we'd spent at peak $549.72 an hour, and the total cost was $4,362 all in to basically borrow that class of environment for several hours to run some real science.
So I know, Jason, you can't talk too much about your client, but certainly any Big Ten pharmaceuticals got plenty of compute power in-house. Is that the number, that 4,000? Is that sort of attracting them to try this kind of a project, or is there more to it than that?
That's a great question, Rich. So there's the way I like to think about this is it's very similar to the horseless carriage in the car. So when the automobile first came out, people referred to it as the horseless carriage, and cloud HPC is very similar. It's treated very much like what you were doing yesterday, but you don't have to feed the data center, you don't have to care for it, you don't have to clean up its crap. There's sets of aspects of running cloud HPC that are seem similar to what you do day to day, and in fact, most of the customers we have on a regular basis are running between 40 and 1,000 cores. So they're not running these really large-scale environments. But almost universally, each and every one of them at some moment has had a calculation, basically a question that they're trying to answer, that is more than they would ever be able to accommodate on that internal infrastructure or on those smaller, cloud-based environments. So the real piece about this is, although the cost is important, it's the compression, it's the cycle time, it's being able to react faster from the moment you ask the question to when you get the result back. And so just like horseless carriages, where before the car you couldn't travel more than 50 miles in a single day because a horse would die at that point. After the automobile, millions of people can commute, less than that, more than that, into the New York City area reliably. This is the kind of transition point that we're talking about. So with this large pharma, it wasn't so much that the cost was lower, which it certainly is then, from a comparative standpoint, but also that, to run this internally on the idle compute that they had available would take, months to perhaps a year to actually get this done. And so being able to instead do that, submit it one day, and 11 hours later have it completed and have a result the following morning is a huge game changer in terms of productivity, in terms of actually being able to ask the right question and get the right answer that you never would have been able to do before. So this is actually enabling better science, bigger questions, the questions that are the right ones to answer, and not just the ones that might happen to fit on the amount of resources you have available internally. And so that I think is really the key point here. It's about access. Most everyone now can get access to high performance and high throughput computing at scales that in prior years you had to be a government agency and get a time allocation on them in order to do this. And now we can do it in very low cost at very reasonable access points. And I think that's the big changer. It opens up whole new paths to getting computational science done.
So as we look at that, Jason, certainly an Amazon instance like you used is good for some problems, but it wouldn't necessarily work for everyone who might need maybe lower latency or more memory bandwidth, that kind of thing, correct?
Yeah, so there are applications that don't behave as well on cloud as they may internally, and there's always an interesting set of analyses go there. We've had some customers that have we've actually seen a workload that I'm hoping to publish publicly that's an MPI workload at heart. They actually have kind of an interesting high throughput, high performance use case. So they have a large number of Monte Carlo analyses on the outside, and on the inside they have about a 600 core MPI-oriented application that normally when they started looking at it initially, their gut instinct was, we need quad data rate InfiniBand because that's what we use internally in order to run this application. We actually ran it on CC2 instances which have full bidirectional bandwidth at 10 gigabit between all of the nodes in a group, a cluster. And essentially, we found that the application is actually 40% faster on the Sandy bridge with the full bidirectional than on their hardware, which was probably not Sandy bridge. It was probably a little bit older, on their QDR network internally. So the only thing I guess I would observe, and the point of that illustration is just that the only thing that matters at the end of the day is the benchmark, and it's not just the absolute performance number. But it's also the cost. So being able to grab enough of those resources to run 1,200 of those 600 processor jobs that take multiple days a piece to run and get that time to result down is the other factor to this. So it's not just the absolute performance, but it's also the cost per unit science. We frequently see that the cloud does very well on being able to access large amounts of resources that were unplanned for answering big science questions, essentially. And so those are the two kind of prongs to this. On the flip side, though, you're always going to have your applications like the one that I know you guys reported on around Stanford and the million core environment that's obviously a government level system normally used to benchmark the simulation of nuclear devices over long periods of time, et cetera. Those class of machines are obviously have their place, and they do a great job at what they do. The important thing to recognize with Cloud HPC is it's a different kind of capability, but it still is a capability machine. It just has different properties than the capability machines that also have their place, but are the very high interconnect, et cetera.
So Jason, just to wrap up here, I think I like your analogy about the horse and buggy, right? But where would you characterize cloud for HPC in that kind of a span of time? Like, are we on the frontier, just learning what's possible, or are we farther down the road than that?
Well, so I think this is a great that's actually a great question. We're still riding the horse. In certain respects. So I think, there are definitely some people that are still saddling up, but there's also a good number of folks that are are turning the crank on the motor and getting it started. So I as opposed to 5 years ago when we first got started doing cloud HPC and people looked at me like I had three heads. We actually have, a majority of the top 20 pharma. We have a large number of insurance, financial services, and other very large corporate workloads. Most of the growth in volume computing or technical computing have been in the areas of data parallel and high throughput workloads. So if you look at everything from Monte Carlo simulation, which is the high throughput, high performance, MPI on the inside, on the outer for loop, it's a lot of Monte Carlo, through financial services, instrument pricing, financial instrument pricing and risk management, hedging simulation, through life sciences with genomics and clinical trial simulation and proteomics and computational chemistry. All of those areas primarily are high throughput workloads. So they aren't the kinds of things that are that things that simulate nuclear devices are good at. They're actually things that cloud tends to be really good at. So what we've observed is every time we announce one of these large environments, we actually find large numbers of other users that are effectively coming out of the woodwork and realizing, hey, I have a problem that's just like this that I've always laughed at, that I'd never be able to answer it, but it sounds like now I can. So I think we're still on the horse, but there are a good number of people. As you're going along the road on the horse, you definitely see quite a few automobiles out there as well, and I think the ratio is changing. So especially as newer GPU-enabled machines and others become available on cloud, we'll see a lot of interesting use cases come out of the woodwork. But in the short term, Cycle is definitely very excited because our growth rate has been accelerating. We're actually hiring if anyone needs, and we'll be posting something on the insideHPC job board. But essentially, we've been growing so much in this area that we're actually looking for everything from system administrators to software developers to sales engineers, and this is all off of customer demand. So our vantage point is that the growth rate is great in this area. The high speed interconnect machines still have a great place, and they provide a very valuable function. This is just a different kind of capability machine that's getting enabled, and so it has its own place in the ecosystem, and we're definitely happy to be filling that.
Well, Jason, I guess I should congratulate you on this accomplishment, and I want to thank you once again for coming on the show today.
Thanks for having us, Rich. I love your reporting on everything in this industry. I don't know where we'd be without it, so it's always a pleasure to be here. Thank you very much.
Well, thank you for that. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on the world of high-performance computing.